Hi everyone, I'm Jie. This is Ray. Today we are going to present SlabCity for query optimization using program senses. This is joint work with Yuxuan Zhu, Cong Yan, Bazan Mozaffari, and Qinyu Wang. SQL is everywhere, but not everyone can write good SQL queries. We need to transform poorly written queries into the forms that are easier for the query optimizers to further optimize. This technique is query writing. It basically transforms the original query into an equivalent but faster one. It is a critical step in query optimization. Common rewrites or transformations include subquery on nesting, filter predicate move around, group by push down, join elimination, and etc. In this talk, we use transformation and rewrite interchangeably. And these transformations are defined by rewrite rules. A rewrite rule specifies an input pattern, an output pattern, and the constraints on which the transformation is valid. Actually, most query writing techniques are based on rewrite rules. Commercial databases like Oracle, open source databases like Postgres, they all use rewrite rules. Though which set of rules to use or how to apply those rules may vary across databases. And there are some recent works that continue to develop rule-based query writing techniques. For example, Witune can automatically discover and verify rewrite rules. Learn Rewrite focuses on finding the optimal order of applying rewrite rules, and Query Booster can provide a rule language for user to define their own rewrite rules. They all rely on rewrite rules. Then what are the problems with using rules? Given a query queue, by applying rewrite rules, we can get different queries that are equivalent to the original one. They formulate a query space shown in blue color. This query space is a subset of the entire query space. Now the question is, what if the high-quality rewrites are not in the query space defined by the rules? That is, the best query rewrite Q prime is outside the blue region. We know that decades of efforts has been spent on discovering rewrite rules. You may wonder why the rules are still insufficient. Should we have discovered most of the rules already? Let me give two motivating examples. In this example, the goal is to write a SQL query to find the second highest salary. So Q1 is not manually crafted by us. It is written by a real LeetCode user. Q1 can return the correct result. So it first forms an expensive nested loop join to exclude the highest value, and then pick the highest value from the remaining part, which is indeed the second highest. However, this one is not that efficient, and there is a better way to do this. Q2 first picks the max value from the table, and then use it as a filter predicate, and then pick the highest from the remaining, which only requires 2 scans. Unfortunately, no existing rewrite rules can transform Q1 into Q2, though Q2 is more than 100 times faster than Q1. So here the point is, rules do not work well for unseen patterns. We cannot design rules for query patterns we haven't seen. We never know what slow queries written by user look like. And here is another example. The goal is to calculate the running total, more specifically, the running total for each gender on each day. Assume that no index is available. Here, Q1 uses a self-join. This self-join can be very costly, and in very large datasets, you could exhaust all available memory. And here, Q2 uses when function. It can accomplish the same thing, but without the need to use join. And Q2 is more than 10 times faster than Q1. Similar to last example, no available rules can rewrite Q1 into Q2. By looking at these two examples, we know that we cannot design rules for unseen patterns, and the rules can be insufficient in some cases. And now imagine that you have a set of queries and you know they are slow. You have tried rule-based query optimizers, but they fail to work. A natural question to ask is there a way to efficiently find the high-quality rewrites that are missing in the rule space? Our idea is to directly search equivalent and faster queries in the query space. Next, Ray will introduce our framework.
Thanks, Jie. So now let me give an overview of how SlabCity works. Given a slow query, it will be sent to our query synthesizer. The query synthesizer will search equivalent queries in the entire query space. When query synthesizer generates a query, it will be sent to the equivalence checker. The equivalence checker will check if the candidate query is equivalent to the slow query. If it's not equivalent, the equivalence checker will provide a database on which two queries have different output. We call this database a counterexample. And it will be sent to Query Synthesizer to guide the future search. If it passes the equivalence checker, then the query will be sent to the performance ranker. This search and checking procedure will continuously run until it reaches the given timeout. Then the performance ranker will rank all equivalent queries and pick the top ranked queries. And SlabCity will return the queries as the optimization output. The three components in the gray box build the SlabCity framework. From a user's perspective, the user only needs to provide a slow query together with its schema and integrity constraints. Then the user waits and checks the optimization output and chooses the best one to use. In this talk, I will focus on our query synthesizer. Designing a good query synthesizer is challenging. Given the query language, we can imagine that a query space consists of all grammatically correct queries. This space is infinitely large. Query synthesizer searches candidate queries in the entire query space. The biggest challenge is how to search efficiently. Rule-based rewriters can be viewed as synthesizers because they try to rewrite queries in predefined space. There are existing techniques like learned rewrite and Waytune. Their search space is defined by a set of predefined or learned rewrite rules. However, there are some limitations. Those techniques heavily depend on the quality and quantity of the rewrite rules, and they cannot optimize unseen patterns. This basically means the search space they're considering is very small. Because of this, they may lose many optimization opportunities. There are also some existing synthesizers that are not restricted by a set of rules. However, to our best knowledge, those synthesizers only search locally. For example, SEA only optimizes predicates, which are essentially where clauses, and FGH-Rule only optimizes recursions. Again, these approaches are only able to search locally or specific parts of the query, and they're not capable of doing whole query optimization in general. To overcome the difficulties from previous techniques, our approach is whole query synthesis guided by data flows. Whole query synthesis means we search the entire query space, and data flows can make our search efficient. In the next few slides, I will introduce you what are data flows and how we use data flows to guide the search. Data flows captures how data is computed and used in the query. They can be extracted from any given query. I will use this example to illustrate how we extract data flows from a given query. We first focus on the select list. Select list tells us where the output columns come from. In this select list, there are three items. S1.gender tells us that this column comes from the gender column of the scores table. S1.day tells us the column is from the day column of the scores table. And sum S2.score tells us that this column comes from the score column of the scores table, and it goes through a summation. We formalize those using data flows, which are underlined. We can analyze other parts of the query and obtain data flows similarly. For example, join condition tell us which columns are used and compared. Where predicates also tells us what columns are used and compared. And group by clause tells us what columns are used and do the grouping. As you can see, each query consists of multiple components, and we can extract a query's data flow by combining the data flows of its components. Our observation is that for two equivalent queries, they often share a same set of data flows. For example, they both used the gender column. They both used the score column after summation, though one used as an aggregation and one used in a window clause. They both used operations that compare day column to itself. One used auxiliary predicates and one used an order by clause. Though they're syntactically different, their semantics both involve comparing columns. Our key insight is that since equivalent queries often exhibit similar data flows can be used to guide the search. We define the cost for queries using data flows and use such cost in our search algorithm. Given a slow query, for any query component C in the query space, we define the cost of C to be the number of data flows in C, but not in the slow query. This means more data flows in C that are unseen in the slow query, the higher its cost will be. Here are some examples of low-cost queries. On the left is the slow query. We omit the other parts and focus on the sum in the select list. Some low-cost queries are shown on the right. They both used the score column and applied summation on it, though their syntax and actual operations may be different. For example, one used a window and one used a nested query. Here are some high-cost queries given the slow query. We use the same slow query. On the right are queries with high cost. They both exhibit some unseen data flows comparing to the slow query. For example, the first query applied average on score column instead of summation, and the second query applied summation on ID column instead of score column. Using data flows, we can determine that these queries are less likely to be equivalent to the original query. Thus, their costs are high. After defining the cost function, our strategy is to search queries in ascending order based on cost. A key advantage is that we can prioritize the search of queries that are more likely to be semantically equivalent. For the algorithm details, please refer to our paper. From the beginning of the search, our search algorithm can ensure that we first exhaust the query space with cost 0, then space with cost 1, then space with cost 2, etc. Since we exhaust program space by cost monotonically, our search is complete, which means that as long as there exists a query that is faster, we will eventually find it in theory. Since we prioritize queries that are more likely to be semantically equivalent, our search algorithm is efficient. For evaluation, we try to optimize queries in 4 different workloads: LeetCode, which consists of user-submitted queries, call-set rule testing pairs, TPC-H queries, and TPC-DS queries. We also evaluate SlabCity against 2 baselines, learned rewrite and waittune. In the evaluation, we set 5-second timeout for SlabCity. We evaluated the query latency by executing them in PostgreSQL. We run the following experiment. We let each tool optimize every query in every workload, and we gather query latencies on randomly generated datasets of various sizes with different data distributions. The major results are, in terms of optimization coverage, SlabCity can optimize more queries. In terms of latency reduction, SlabCity can find faster queries. And detailed statistics can be found in the paper. Thank you, and this ends our talk.